It's great to be here talking about NDN for the afternoon. So I think I will try to illustrate the basic concepts by some very simple examples. But still, NDN, the named data networking, is a very different way to think about networks. And therefore, I think the first time you hear about it, I'm sure you're going to have many questions. So what is NDN and why do we do NDN to start with? If you haven't heard about, this named data networking actually started in 2010. It's almost 10 years now. The question is why we need a new network. So I want to explain through very simple examples. So what the network really does is deliver your data. Think about this simple illustration of multiple entities, maybe all mobile, especially in battlefield. You cannot drag a cable going around. And therefore, the goal is really get recorded data delivered reliably, resiliently, and securely. But how do we do networking today? The networking today is accomplished by an IP delivery. And the IP has a very simple model. Deliver packets from point A to point B, as I marked out there. How do you identify those 2 points? By IP addresses. So to IP's view, the network is just a collection of point-to-point links. Then the network has this job of routing, which is to find a path by concatenating a number of these links. So you make an end-to-end path, and data will be delivered over that path. Now, what are the issues? We all know what the issues are. There's the nodes that moves, the links that fail, and the connectivities that change. In particular, those are the features in the battlefield. If I add a comment here, you may say, how come IP wasn't designed to handle this? We need to give the IP design, we need to look at it in the perspective view. That was 40-some years back. UCLA just celebrated Internet 50 last week. Back then, how many computers in the whole world? A very, very small number. So the goal of IP at the time was just connecting computers together, connecting remote terminals to the IP. That was entirely different world. That's how people designed IP to fit the need of the day. And also the technology in those days, there was no wireless communications. There is maybe satellite, but that's a very static. Not like today's, you carry your phone moving around, you have a vehicle that has a Wi-Fi connectivity, etc. So the world has changed. So the world has changed, and the old technologies no longer fit today's need. Now the question is, how do we solve them? So the Einstein quote here by saying that we cannot solve it by continuously to think in the IP way, how we deliver packet from point A to point B. That will not work that well. So the years back, I mentioned that the NDN project, almost 10 years now, actually the first talk in this direction of research was given by Van Jacobson in 2006. The title of the talk is A New Way to Look at the Networking. Essentially, he brought up this idea to say that instead of naming the nodes and then we deliver packets to that destination address, let's just focus on the data. Given, like I mentioned in the previous slides, the network is to deliver the data. Why can't we just focus on the data directly? Name the data piece, and you can just request for data. Here, I give an example to say that now we're at MILCOM, and that's really the URL to the MILCOM page. That's the name of that HTTP object. So if you just give that name, you can get into the MILCOM front page. Think about it's really a data object. It really is. It's an HTTP object. And therefore, think about if you captured by your smartphone, yet supposedly the MILCOM website will sign the data. And then this piece of data can be delivered to whoever requesting it. Say that there's multiple parties who wants to receive this piece of data, not in this well-connected infrastructure-based MILCOM network, Hilton network, but instead in a kind of ad hoc mobile environment. Only one cell phone had this data object. Other parties can just retrieve it. The key point is that one can send a request for data as long as you know the name. But do we know the MILCOM name? I mean, the website name. We do. You just, by the naming convention. So the MILCOM is let's say, this is fc.org, right? You can go there and you can find the further longer the file names for that. The key point is that when you request the data, you are not asking any specific nodes to give you the data. Instead, you throw your request into the network to say, hey, who has this piece of data? This network's responsibility to find the matching piece and deliver to you. When the data gets delivered, you can do the validation, check the signature to see if you get the valid data. And that's really the key point. It's very different from what we do today. Today, either the web service is not secured, otherwise you secure it by securing the TCP connection. But the TCP connection connects to an address. How do you validate the address? Well, you have to do the translation from names to addresses, and from that name, you have to check with your, they call the CA, certificate authorities, to verify the name. The question is, how do you know that the CA is trustworthy? How do you know it? Well, the CS key, I think people all know that, the CS key actually get into your browser through the back door. That's all done by your browser vendors. They secretly create this called a root file that collected all the certificate authority website's key and put into that root file. Whenever you do the browser updates, they give you updated root file. I just heard, if I added one comment, over the weekend, some conversations, Saudi actually had tried to buy themselves into the root file by acquiring some companies that already had a key into the root file. I was thinking this is really, really, really scary. That is, I don't get to manage my trust anchors. That is, whatever the certificate in the root file. Instead, somebody else manages it. If you can get data from anywhere, when I say data goes through the network, it doesn't mean just one hub. It can be multiple hubs. And you don't know who are the guys, who owns those nodes, who forwarded the packets. Therefore, the critical point is really like, once you receive the data, you must be able to verify the authenticity of the data packet. I would just give you an example to illustrate the fundamental differences between your request data by name versus what we do today, that is you shoot the IP packets to the destinations. So in this case, let's see how the IP delivers packets. Say that the soldier carries a camera and you can capture the videos, and someone else, supposedly by some magic, learns that there's a data available, this party needed, so they're gonna ask for the data. Exactly how you ask, that still requires some services. I just ignore those details. I want to illustrate what happens at the network level. So first of all, each of the parties in the communication, they need to get the IP addresses. Now, in a very dynamic environment, where do you get IP addresses? And what does the IP address mean? In a static environment, like we sit here, the computer connected, of course you have an address. Address is an attachment point to the infrastructure. But in the battlefield, the address actually doesn't have a meaning. At the most, it becomes a unique identifier. But say that the packet goes from the source to the requester. It's going to go to that router I shown there. It's going to stay in the buffer and then get delivered. But notice that this packet identifies the receiver's address. As soon as the router sends the packets out, it will delete it from the buffer. Why? Because it's no longer useful. That packet only has one meaning. That goes to that destination. If you save it, say that you have the memory. Nobody else could get it because it's not for anybody else. Therefore, if there's a second soldier nearby and asking for the same data, what happens is that the source had to send it a second copy. That's the difference. So IP is really one point to another point communication. Now, if we do the same thing through the NDN network, what happens is that you can request for data. It's really explicitly designed into protocol. Name the data networking really means you request data by name, and data will be delivered by name. When you request data, reach it to the source will send the data back. You can look at this data. It has a name. That's whatever the thing you ask for, the contents, and there's a crypto signature. The fundamental difference between this packet and that IP packet is really the identity carried in it. This name identifies the content. It does not identify who should receive or who should not receive it. So therefore, when the router, the NDN router receives it, it can buffer it for whatever time period it feels appropriate, because the data packet stands on its own, independent from who requested it. So therefore, if the additional parties asking for the same data, this data will be fetched from the router buffer. Let me just say one more time. I know it's a simple concept, but NDN packet is identified by its name. It's independent from the nodes, where it comes or where it goes. So therefore, whoever requests this piece of data, the intermediate nodes, you can think it's a host, the routers, or any carrier. If they have the data, they can supply and satisfy the request. IP routers today, I tell you, got a lot of memories because technology advanced, but they cannot buffer the packets simply because the packets is identified by that single destination. And so therefore, nobody else can make use of that packet towards the buffering. In particular, I would just want to mention one thing. Say that if that IP packet gets dropped over the last hop, and packet need to be retransmitted, where the retransmission come from the original source. So in today's TCP/IP, all the losses have to be recovered end to end, simply because the data itself has no identity. Even if you had a copy in the middle, nobody knows what that is. Now, once you name the data, you get other advantages. Here I'm illustrating to say how you can accommodate the data mulling. Because now data gets named, and it can be cached by anyone, by a static router or by a moving entity. So here we say that, okay, the data got produced and get captured by a zone. If the zone moves, it carries the data to whatever the headquarters. If the headquarters notice that there's a signal there, zone is coming back, you can request data and I got it. And the zone can further fly to some other locations where the request data is needed. Notice that this is just one protocol. Request data, you give data, and data is secured on its own. So therefore, the data security does not depend on the carrier security or the channel security or the locations of anything. Now, how we do all of this magic by the simple protocol is like in every node that runs NDN, internally it has a few modules. There's the cache, you can already heard about it. It's called content store. And then there's the forwarding information base as a FIB. That's what every router, IP router has as well, to decide if you receive a packet, given a destination address where you forward it. But in the middle, there's this box called the pending interest table. What does a pending interest table do? I'm going to illustrate later, and how. And also, there's another box called the forwarding strategy. I will also explain in due time. So look at the FAPE. The FAPE on the surface more or less look the same, like an IP FAPE, forwarding information base. It has destinations. Well, here it's not destinations; it's a name prefixes, and then there is a next hop which interface you should forward it to. But there are some fundamental differences from the IP FAPE. The first one is that how you create this one, how you create the FAPE. You can use routing protocols. That's how IP FAPE gets created. And here, we can run the routing protocols over NDN network. We can also have other means to fill in the FAPE. One thing is called self-learning. That is, you just see the packet flowing by, then you remembered in which direction the data comes, you can put it in. This is very similar to the link layer self-learning. When you do the Ethernet switches, you don't run routing protocol per se, but you just observe which address coming from which direction. Next time you receive a packet with that MAC address as a destination, that's what you forward it to. It's a similar idea. You can use that to build a FAPE for NDN network. There's also another difference. The pending interest table, I'm going to explain how they get filled in later. But fundamentally, every time you forward a data request, we call the interest, you actually put a copy into that pending interest table. That's why it's called pending interest table. Why you need that? That will be needed to get the data back. You need to know which way the request comes, so the reply will go back the same path. With that, that is, you keep a copy of all the requests. That means that the request cannot loop. If you receive an interest, you have seen it, oh, it's in my pending interest table already, you drop it. So there's no looping possible. With that, the FAPE is kind of relieved from the worry about routing loops. That enables it to more easily explore multiple paths. So let's run the example. There's some users send a request for some certain data. First thing this node will to check, do I have a cached copy of the data already? If so, return it, you're done. If not, you ask the question, have I seen the same request? That is exactly the same name for the data. If so, if you have a pending interest for that exact same request, that means you have forwarded that request before. So therefore, for this new request, you just need to know from which interface it came in, and then you're done with it. So you can see that that's what shows up in the pending interest table. There's a interest name, where it comes from, and where it goes out at what time. But if you fail the first two checks, then you look up the FAPE to say, okay, this is the first time I saw this request. Where do I forward? You consult the FAPE to figure it out. But there's a difference in that, the difference from IP. For IP, it's a single pass forwarding, one way only. Even though today the network connectivity is very rich, mesh connected, but you only can forward to a single pass. Why? You worry about loops. The single pass is nailed down by the routing protocol. They shouldn't loop. But in the NDN, because the interest packet cannot loop, therefore you're free to forward to one or multiple interfaces at the same time. Of course, you don't forward all the interest to multiple interfaces. You forward to multiple interfaces when you don't know for sure which one is the best one. Then you wait to see which one actually returned the data packet back. Then you can stay with the working one. The point here is that you are free to utilize multiple interfaces, and you can switch among them. So when data comes back, I already mentioned, now it utilizes for pending interest table. The first thing the router this node gonna ask is, hey, did I ask this question? That is there matching entry in the pending interest table? If so, I ask the question, I'll forward it according to the pending interest table. If I didn't ask for this data, I'll just drop it on the floor. So you cannot DDoS NDN nodes by flooding the data packets. The data, unrequested data, will not be forwarded. The DDoS prevention. Then say that you find the forwarding, you find an entry in the pending interest table, then you see how long it takes to get it back. Because in that table entry, you recorded when the interest went out. So you automatically get the measurement for the round trip time. This is built into the protocol. And from the round trip time, and based on how many interests you forwarded in that direction, you can estimate the throughput as well. So measurement is fundamentally designed in. Then you forward it to all the incoming interfaces that you received that same request. What is this thing? This is called the multicast delivery of the data packets. We haven't done anything different from the protocol, but you can see that multicast delivery is a very much needed functionality for the internet. And we tried so many years. It hasn't been widely deployed. For this protocol, through that simple data structure on the nodes, you can deliver that functionality. And then you can also put a copy in the content store as a cache, and then you return to the users. When I said, okay, you look up the FAPE, decide where to forward it, actually, the decision is more complex than that. Because FAPE only provides one of the input for your decision. What other input do you have? The measurement results that are recorded in the PID. So it's not only, okay, go through this way, you can get the data back. But also you say that maybe there are 2 ways or 3 ways. Which way is better? You have the measurement result give you a guide to say, when I forward a future request under that same name prefix, which choice I'm gonna make. And also, you may have some policies to say more important data will go out one direction, less important data go the other direction. So that's the policies based on the whatever captured by the forwarding strategy. Based on all of this, the forwarding strategy actually makes the decision on precisely, given an incoming interest packet, which way or which ways I'm going to forward it. Battlefield required resilient data delivery, right? What do? We can do host multi-homing. My phone has multiple interfaces, Bluetooth, Wi-Fi, send packets out in all directions, say which way it's going to work. We can do multicast delivery, and we do pervasive in-network cache to make the data more available. That's what the CDN's content delivery networks are doing today, like ICOMA, like Limelight. We need the delay disruption tolerance support, so people have developed the DTN protocol for that purpose. Then we need to do multi-pass forwarding to try alternative paths. And IETF has been working really hard. I'm an old IETF goer, started from IETF #1 for so many years. So there's lots of work in exploring the support for all of that. So all of this is about redundant ways to get the data. That's how you can have resilient communications. Now, like I mentioned, that this can be done by IP. There's nothing cannot be done, really. Computers can do all the magic. The fundamental thing is that each of these has been explored for many years. Each of them got resolved kind of in isolation from all the other goals. And you have to tweak the protocol in a certain ways to make it work. What the NDN does is that all of this functionality is accomplished by that same basic protocol. By the same basic protocol, host multi-homing. I mean, your phone has multiple interfaces. It doesn't really matter which way the request comes in, I just send things out. When I send the request out, I can send in all the interfaces out. Because the data names It's independent from which interface the packet may go in or may come in or going out. The multicast delivery, like I already mentioned, is built in, and delay disruption tolerance, I illustrated that as well. So all of this just requires that you name the data and you have to secure the data directly. And therefore, the delivery will be independent from the locations, the paths, whatever other things. Now, security. So how do we secure the network today? Since the early days, TCP/IP didn't have security. When security became independent, we put the patches on. IPsec, the TLS, SSL started with. Even the latest protocol, like a QUIC, the QUIC UDP internet connection, they all follow the same thing. That is, verify the destination through the certificate authorities, then you secure the channel, the delivery channel. So this works if you have good paths. If your path comes and go, you cannot have a secure channel to start with. And you need this certificate authorities service to be available so that you can verify whom you are talking to on the other end. Certificate authorities has their own problems. I'll save that from some later time. But in the battlefield, this is synchronous communication. That is, you have working paths. That's simply not a very good assumption to start with. And require the infrastructure support, that is, there's some servers you can always reach in a reliable way to fetch critical information about, verify the certificate of the party you want to communicate with. This is also not realistic. So NDN, like I mentioned, you secure the data directly. So that you can enable secure communications independent from the paths. It can be delivered by the data mules, etc. And you can just verify the data when you get it. So all this requires is really like all the parties need to have a certificate that can be verified by the receiving end. But this makes the communication totally independent from intermediate entities. Say that now in this case, if the two ends are not really fetching the data directly, but instead maybe there's a chip in the middle, it captures the data, and then from there it gets forwarded to the recipients. It still works. So all we needed is security bootstrapping. They need to have trust anchors to verify certificate. And all the data producers need to have certificate so that they can send the data. Conceptually, you say you need data authenticity. Well, crypto people told us you can send the data. You need the confidentiality encrypted. And you need availability. Well, redundancy saves your day. You can make multiple copies. You can deliver the data through multiple passes. So for this availability, I just want to repeat it one more time. All of this actually built into the protocol. And then just does it. Now, for the first two, the signature and encapsulation, that really requires the management of the keys. So the trust management, that is how you get the keys, get the right keys in a reliable way. And the second thing is the usability. We as human beings, how smart we are, I don't know, but we're not made to manage crypto keys. I'll just say this way. That's why crypto protection has been very difficult to deploy today, because it depends on human to manage those keys. So trust management today is through centralized commercial certificates authorities. NDN's approaches have local trust anchor. What do I mean by local trust anchor? I give you an example. I'm from UCLA. So UCLA pays my salary, hires me as an employee, and UCLA can be one of my trust anchors. How do I get UCLA's key reliably? Well, we have many ways. They pay me in a reliable way. So we can have local trust anchor. And then the next question will be, Berkeley is a local trust anchor. UC Irvine is a local trust anchor. Then the trust question becomes how you establish relations between those trust anchors. I want to say that this idea of having local trust anchors, then establish connections among them, the trust relations. This is not our idea. Who came up with this idea? This is actually called SDSI, the simple distributed security infrastructure, proposed by Professor Ron Rivest of MIT back more than 20 years at MIT. How come it didn't get deployed? Long story. Essentially, is that there's no tools to have local trust anchors back then. Yet the commercial market just instantly say that, here, me, I'm your trust authority, pay me, and I issue a certificate. Usability. You need to have comprehensive policy configurations, allows users to configure things in a people's way, people-friendly way. Then the key management, you need to design a system that can automate the key management. So that's the secret sauce. Just take away is that NDN is really fundamentally different way to communicate. You name the data, you just fetch the data. And that has a number of advantages and provided functionality that we've been looking for many years now and have not succeeded that well. And for securities, I will leave to Alex to go after me. And here we included a few references in case people are interested. That will be in the tutorial slides. Thank you very much.